Hello, and welcome to another edition of Mr. Chappell's Chemistry Screencasts. Today we're going to learn about calculating equilibrium concentrations. What you'll learn today is how to calculate the equilibrium concentrations of reactants and products. Now there are a couple of things you're going to need. You're going to need a calculator, of course, and you're going to need to know how to set up the equilibrium expression. And you're going to need lots of time because these problems take lots of time. Let's go ahead and get started. Okay, here's our first problem. And we're being asked to find the equilibrium concentrations of everything after equilibrium is established. So I think the first thing we want to do is go ahead and let's rewrite the equation so we can make a little table. And we're starting out with carbon dioxide. And we're adding hydrogen gas. And that is in equilibrium with carbon monoxide and water. So what we need to do is make a table where we set up our initial concentrations. Then we need to figure out what kind of change is going to be going on. And then finally, we're going to get our equilibrium concentrations. So we're told in the problem that we're starting out with initial concentrations of 0.1 molar. And we have no concentrations of our products. Next, we need to figure out what direction the equation is going to be going. Well, we're only starting with reactants, so their concentration is going to decrease, since that's the only way the equation can go. So we're going to take away X from the carbon dioxide, we're going to take away X from the hydrogen, and we're going to get produced X for carbon monoxide and then X for water. And you would best be served if you take the balanced equation and you just put the coefficients, if there are any, in front of your X. And the coefficients here are all 1, so it's going to be 1x for each of these. So that means when equilibrium is established, we're going to get 0.1 minus X for this reactant, and the same thing for the second reactant, and then finally X for each of the products. So let's go ahead and write down our equilibrium expression. And the equilibrium expression, K sub C, is the equilibrium concentrations of the products over the reactants with the coefficients raised as exponents. Now let's go ahead and substitute in our values, and so we're going to end up with x squared upstairs all over the quantity 0.1 minus x quantity squared downstairs, and we're told that that is going to be equal to 0.64. Okay, now at first brush you might think we need to go through the quadratic. Well, not really with this thing, because what we can do is we can take the square root of both sides And what we end up with is 0.80, and that's going to be equal to x all over 0.1 minus x. So now what we need to do is we need to solve for x, and I'll just go ahead and do that really quickly. And if you solve this successfully, then what you should get is 0.044 for your value of x. Okay, well, we're not done yet. We started out the problem by saying that our concentration, equilibrium concentration of carbon dioxide was equal to, or will be equal to, concentration of H2. And that is equal to 0.1 minus x. And that is going to be equal to 0.056 molar. And then lastly, we said that our concentration of carbon monoxide is going to be equal to our concentration of water, and that's going to be equal to x, which of course is 0.080 molar. And that is our final answer for this problem. Okay, here's our next one. And let's go ahead and just set it up like we did for our first example. This is Mr. Knight. Whoops, sorry about that. Okay, here's our next problem. And let's go ahead and set it up just like we did for our first one. Let's rewrite the equation so we can make a little table. And we've got Mr. Nitrogen plus oxygen, and that is in equilibrium with nitrogen monoxide. And we've got initial, change, and then final. And we're told that we're starting out with, for Mr. Nitrogen, we're starting out with 0.04 molar, and for oxygen, 0.01 molar, and we have nothing of the product. And we're going to be taking away x, and taking away x from the oxygen, and then we're going to be adding to the product side 2x. Your best bet is just to steal the coefficient and put that in front of your x. So when equilibrium is established, we get 0.04 minus x .01 minus x, and then finally 2x for the product. So when we write our equilibrium expression, K sub C, it's going to be products over reactants with the coefficients raised as exponents. And now what we can do is we can substitute in our values. Going to be 2x quantity squared all over 0.04 minus x times the quantity 0.01 minus x. all that is going to be equal to the equilibrium constant, which for this number is 1.0 times 10 to the power of negative 30. Now, you'll notice that we have a second degree polynomial, and it looks like you're going to need to go through the quadratic, but let me show you a little trick. We know that the equilibrium constant is very small, 10 to the power of negative 3, last time I checked, negative 30, sorry, is very, very tiny. So probably when we take the difference between our starting concentrations and x, whatever it ends up being, if we follow the rules for sig figs, those concentrations are going to remain unchanged. In other words, x is negligible. So what I can do is I can just assume that this x isn't going to matter, so I'll go ahead and cross it out. And what I get, let me go ahead and rewrite that. I get 4x squared all over 0.04 times 0.01. And that is going to be equal to 1.0 times 10 to the power of negative 30. Okay, well this you can easily solve. You don't need to go through the quadratic to solve it. And let's just go ahead and figure out what x is. And by my calculation, I get that x is going to be equal to 1.0 times 10 to the power of negative 17. And so that value is actually very small. Now, you do need to go back and check and make sure that x is indeed negligible. And the rule is that your value for x, this x, needs to be 5% or less than 5% of your starting reactants. Well, we can certainly do that, but you know, I can just by inspection looking at that, that is going to be way, way, way less than 1% or 5%. So when we started out, we said that the concentration of N2 was going to be equal to 0.04 molar. And we said the concentration of oxygen was going to be equal to 0.01 molar, and those are going to remain essentially unchanged. And then finally, our concentration of nitrogen monoxide, we said it was going to be equal to 2x, and that means it's going to be equal to 2.0 times 10 to the power of negative 17 molar. And that is our final answer. And essentially what you're saying is not a whole heck of a lot is going to go on with this reaction. Okay, for our last example, save the best for last. Let's go ahead and, well, let's make our table like we did before. And so we've got dinitrogen tetraoxide. And let me go ahead and get the right color here. Dinitrogen tetraoxide. And that is in equilibrium with nitrogen dioxide. And we need to set up our initial concentration, whatever change is going to occur, and our final concentration. And we're told in the problem we're starting out with 0.1 molar of the reactant and nothing of the product. So we're going to take away from the reactant We're going to add to the product. That's going to be 2x. So our final concentrations are going to be 0.1 minus x, and then 2x for the concentration of the product. So our K sub C is going to be equal to the equilibrium concentration of the nitrogen dioxide squared all over the equilibrium concentration of the dinitrogen tetraoxide. And if we go ahead and substitute in our values, we get downstairs we get 0.1 minus x, and upstairs we get quantity 2x, whole thing squared, and that is going to be equal to 0.36. Okay, well, there's no way around it in this case. This is a second-degree polynomial. You cannot assume that x is negligible because x is far too large. There's really no choice but to have to go through the quadratic equation. So if we take this and set it up like we normally do for a second-degree polynomial, we would find that we get 4x squared plus 0.36 x minus 0.036, and that is all equal to 0. So now we need to go ahead and plug everything into the quadratic equation, and when we do that, we're going to get two values for x. And when I solve using the quadratic equation, the two values that I get are 0.06 and negative 0.15. Well, the negative 1.5 is not a realistic answer, since we would have to form more reactant and we don't have any product to form it from, so this guy is definitely out. And our x value is 0.06. So when we started out, we said the concentration of the dinitrogen tetraoxide was going to be equal to 0.1 minus x, and that ends up being 0.04 molar. And we set our concentration, equilibrium concentration of the nitrogen dioxide was going to be equal to 2x, and that is going to be equal to 0.12 molar. And those are our final answers. And that concludes this lesson. Okay, it's joke time once again. Hey, did you know that marathon runners that have bad footwear suffer the agony of defeat?